Hello everyone, I'm Asif Iqbal from Michigan State University. Today I'm going to talk about multipactor breakdown in RF structures. This is my final project presentation for the CMSE 802 course in the fall 2020 semester. First, let me briefly go through the outline of today's presentation. I'll start by talking about the motivation of the project, where I'll try to answer the most basic questions such as what is multipactor discharge and why is it important to study multipactor discharge. Then I'll talk about the different mechanisms of multipactor discharge. Then I'll talk about the fundamentals of single surface multipactor discharge, including the electron dynamics and the force law and the secondary electron yield. Then I'll talk about two-surface multipactor, which is the principal focus of this project. I'll talk about its basic concepts and the Monte Carlo modeling of two-surface multipactor. I'll go through the code overview of the project and present the multipactor susceptibility chart obtained from the Monte Carlo simulation. Finally, I'll summarize the talk and discuss a couple of possible future works. The term multipactor stands for the development of an electron avalanche driven by a high-frequency RF field. The avalanche is self-sustained by an exponential charge growth through secondary electron emission from a metallic or dielectric surface. There are two basic mechanisms of multipactor discharge, the single surface and the two-surface multipactor. In single surface multipactor, a metal or dielectric surface is exposed to a high-frequency RF field. When an electron comes out of this surface, it gains energy from the RF field, and when this electron impacts the surface again, it gives birth to multiple secondary electrons through the secondary electron emission process. These secondary electrons in turn impact the surface over and over again and under certain conditions create an electron avalanche. For two-surface multipactor, two parallel plates are exposed to a high-frequency RF field. Primary electrons emitted from one surface gains energy from the RF field, bounces back and forth between two surfaces, and when certain conditions are met, they create an electron avalanche through secondary electron emission. Multipactor discharge can be useful in certain applications, such as for vacuum conditioning and harmonic generation. However, in most RF applications, it's really harmful. It causes many problems such as breakdown of dielectric windows, erosion of metallic structures, melting of RF components, etc. Therefore, multipactor is a major concern for high-power microwave sources, RF accelerators, and space-based communication systems. Now let's look at the fundamentals of single surface multipactor, which frequently causes damages to dielectric windows, accelerator components, and satellite communication devices. Suppose we have a dielectric surface and an RF electric field is acting parallel to the surface. Now, when an electron comes out of the surface, it gains energy from the electric field. When the electron leaves the surface becomes positively charged, which gives rise to a normal electric field. This normal electric field attracts the electron back to the surface. When the electron impacts the surface again, it can create multiple secondary electrons through secondary electron emission. This phenomenon is modeled in three stages: the particle emission stage, the particle in flight stage, and finally the impact on the surface stage. In a 2D Monte Carlo simulation, we assume that particles are emitted from the surface with random emission energies and angles. There are a few distributions proposed by different researchers to assign random emission energies and angles to these particles. One of the most extensively used distributions is given by these equations proposed by Rami, Kishek, and Y.Y. Lau. Here E0 and phi are the random emission energies and angles, and E0 m is the peak of the distribution of emission energies. Then, in the flight stage, the trajectory of the particle is governed by the force law, from which we can calculate its instantaneous velocity and position. In the final stage of modeling, when the particle impacts the surface with sufficient energy, it can create secondary electrons. The number of emitted secondary electrons per impacting primary electron is called the secondary electron yield of the impact, given by delta. When delta is greater than 1, there is exponential charge growth which leads to multipactor discharge. The secondary electron yield depends on material properties, surface topographies, and the primary electron's impact energy and angle. There are several models proposed for calculating the secondary electron yield of an impact. In our study, we adopt Vaughan's empirical model of secondary electron yield. In Vaughan's model, the secondary electron yield of an impact is calculated with these equations for different ranges of impact energy. There are a couple of more equations to describe the effect of impact angle of the impacting particle. With this basic understanding of single surface multipactor, we are now ready to move on to the two surface multipactor, which causes frequent damages to parallel plate waveguides, RF accelerator components, and satellite communication devices. As we said previously, in two surface geometry, multipactor discharge is developed by electrons bouncing back and forth between two surfaces, creating electron avalanche through secondary electron emission. However, this mechanism is a bit tricky compared to the single surface multipactor. For example, suppose our electric field is directed from the top surface to the bottom surface. Let's assume that in the positive half cycle of the RF field, an electron is emitted from the bottom surface. However, the RF frequency, the RF field strength, and the gap distance between the two surfaces is such that before the electron reaches the top surface, the RF field reverses its direction and accelerates the electron back to the bottom surface. It can also be possible that before the electron reaches the bottom surface, the RF field reverses its direction again, preventing the impact of the electron on the bottom surface. From this example, it's clear that for the successful development of two-surface multipactor, the RF field defined by the voltage VRF and the angular frequency omega coupled with the gap distance d need to create a certain resonant condition where an emitted electron reaches the opposite surface near the time when the electric field changes direction, so that the emitted secondary electrons can be accelerated to their opposite surface during the next half cycle of the RF electric field. Of course, the other fundamental condition also needs to be satisfied, which is the average secondary electron yield over a series of consecutive impacts must be greater than unity. We can model this two-surface resonant multipactor discharge with a 1D Monte Carlo simulation scheme consisting of the same stages as those of the single-surface multipactor. In the particle emission stage, we assume that the particles are emitted with random emission energies and angles according to these distributions given by Rami-Kishek and Y.Y. Lau. In the flight stage, the trajectory of the particles are governed by these force law equations. And in the impact stage, the secondary electron yield is calculated using the Vaughan's formula which we discussed before. Now let's ask ourselves, what can be a meaningful goal of our Monte Carlo simulation? What do we intend to find out? We have previously discussed that if a certain RF voltage, frequency, and gap distance between the surfaces cannot give rise to the resonant electron motion, multipactor cannot develop. This is precisely the million-dollar question that we intend to answer. What are the good combinations of RF voltage, frequency, and gap distance so that multipactor breakdown does not happen? The way to answer this question is to construct a plot where in one axis we have the RF frequency gap distance product and in the other axis we have the RF voltage. Each point in this contour represents a certain combination of these device parameters. We run our Monte Carlo simulation for each of these combinations and find out which points lead to multipactor discharge and which points don't. This chart is one of the most useful tools in RF applications, and this is called the multipactor susceptibility chart. In our Monte Carlo simulation scheme, for each point in the susceptibility chart, we run the simulation with 90 different initial test phases of the RF electric field. This choice of the number of initial test phases is subject to the requirement of the precision of simulation and trades off with simulation time. Now, for each chosen phase, we run the Monte Carlo simulation for 10 consecutive bounces. We record the secondary electron yield for each impact, and then we calculate the average secondary electron yield. For any test phase, if the average secondary electron yield is greater than 1, we have multipactor. For the coding part, I have split the algorithm in a few separate functions. First, we have the defined simulation domain function, which specifies the ranges and the number of grids in the contour plot. Then we have the SEY contour generator, which runs the simulation and generates the susceptibility chart. It calls the average ACY calculator function, which calculates the average secondary electron yield for each point in the chart. This function does so by calling a few other functions. First, we have the random emission energy and angle generator functions. As the name suggests, they give a particle random emission energy and angle. Then we have the find flight time function, which calculates the flight time of the particle by solving the force law equations. After that, we have the impact parameters function, which calculates the impact energy and angle of the particle after its flight time. Finally, we have the von model ACY function, which calculates the secondary electron yield of an impact depending on its impact parameters. Once we have all the points in the susceptibility chart evaluated, we use the plot susceptibility chart function to plot the chart. And this is the susceptibility chart that we have obtained from the simulation for parallel plates made of copper. Of course, for different material, the chart will look different. Here, the dots are the points with multipactor, which must be avoided for safe operation of the device. All the other points are good with no multipactor for those specified parameters. In summary, I have discussed in this talk about the mechanism of single and two surface multipactor. I have presented a 1D Monte Carlo simulation scheme for modeling two surface multipactor, and I have finally presented the multipactor susceptibility chart for copper that I have obtained from the Monte Carlo simulation. Future works may include developing 2D or 3D modeling schemes, investigating multi-frequency RF operations, and the study of the time-dependent physics, which may include analyzing particle trajectories and their temporal behavior. I'd like to thank my PhD supervisor, Professor Peng Zhang, the excellent instructor of this course, Professor Dirk Colbury, and also Alizer for helping me throughout this course. Thank you, everyone.